In this video, I want to introduce a few identity properties. The first property that I want to look at is the additive identity. So the question is, if I have a number like 5, what can I add to it to get the number 5 back again? And I think you know the answer to this question. It's simply, if I add 0, I will get 5 back again. Similarly, there's the multiplicative identity. I'll shorten that. ID. If I have a number like 5 and I want to get 5 back again, I think it's pretty clear what we could do to make that happen. We could multiply by 1. So that would be 1 is the multiplicative identity, or will give us the same thing back again. So we refer to it as the multiplicative identity, and 0 will give us the same thing back again when we're doing addition. So we call that the additive identity. Now, this seems fairly obvious, so you may wonder why this is useful. Let's first look at the multiplicative identity, because I think this one is simpler. If I have something like, let's say, 6 over 8. Well, technically, 1 is the multiplicative identity. If I were to multiply this by something like 2 over 2, I'll end up getting an answer where if I multiply the numerator, the numbers in the numerator first, I would get 12. And if I multiply the numbers in the denominator second, I will get 16. And we could say that 6/8 is equal to 12/16. Hence the equal sign, we can put that there, because what we started with on the left is equal to 12/16. It's the same amount. Multiplying it by 2 over 2 didn't change the value of what we're talking about. It just expressed it in a different way. When we're working with fractions, it's often very helpful to change them like that. So another example that's probably working on the same fraction, 6/8, you may have recognized that we could divide both the numerator and denominator by 2. But that's really using the multiplicative identity. Dividing by 2 is the same as multiplying by 1/2. So if we were to multiply both the numerator and denominator by 1/2, the numerator would become 3, and the denominator would become 4. And so we can say that 6/8 is equivalent to 3/4. They're the same amount, the same value. So that's a very useful use of the multiplicative identity. It's very helpful to be able to do that when working with fractions. The additive identity, it's not so obvious when that's helpful, but here's an example. If I had an expression like x squared plus 2x equals 0, this is a little bit ahead of where we are. It turns out that's when we start working with parabolas, we will see things like that. But if you wanted to manipulate this, you might realize that it's actually helpful to do the following. It's not going to be so obvious right now, but if I wrote plus 1 here and minus 1 at the same time, it would still be true, because plus 1 minus 1 is 0. So using the additive identity would allow us to put plus 1 and minus 1, and then we can rewrite the entire expression, I should say equation. And it turns out that what's on the left-hand side is now a perfect square. We'll talk about the meaning of that later. Without adding the 1, it wouldn't be a perfect square, and having a perfect square allows us to do some interesting things that will be useful as well. Now, let me just talk about one more thing that's somewhat related to this, and that is the idea of missing coefficients. So when we get to linear equations, we're going to see that y can be expressed as mx plus b if I want to have a linear relationship between y and x. Now this is maybe a little abstract right now. Let's make it less abstract by giving examples. I could write, for instance, y is equal to 2x plus 3. Or another example would be y is equal to 2/3 x minus 1. So in each of these cases, we've taken a generic expression for a line and we've substituted in actual numbers for m. We'll see later that that represents the slope. So in the first example, the slope is 2. In the second example, the slope is 2/3. We've also substituted in a b value, which we'll later see as the y-intercept. And in the first case, we've substituted a 3. And since it's plus b, in the second one, we could say we're adding -1. So we're adding on -1 instead of think of that instead of subtracting 1. So we've actually placed values in. But it turns out some other relationships could be linear as well. So let me give a few other examples. So if I wrote y equals x plus 3, that would also be linear. You may not notice by just looking at it what's going on. There's no m value. There's an implied 1 for the m value. So it's related to the multiplicative identity. If, on the other hand, I wrote something like y equals 2x, it's implied, if we want to use the same form, that we're adding 0. So it's still in the form of y equals mx plus b, but we're not showing a b value being added. What does that mean? Using the additive identity, the b value must be 0. Finally, we'll see that y equals x is also a line. And in this case, we're doing both things. We're multiplying by 1 by implication. We don't write that we're multiplying by 1, but there would be an m value of 1, and we're not adding anything to it. So we are, by implication, adding 0. And let me just give one last example. We could write y equals 3. In that case, this is really using the 0 property of multiplication, but we have a 0 times the x value plus 3 added on. So it's similar. We're just missing one of the coefficients. It's not really using the two properties just discussed. The missing coefficient, since there is no x showing, must be 0.